Hey guys, so I decided to cut off the second video just because I wanted to clean up the list of strong electrolytes and the list of weak electrolytes. I just want to make sure that you guys have all of the available tools and resources that will allow you to make accurate predictions as to whether or not a specific solute will dissociate 100% of the time, indicating that it is a strong electrolyte, or it will have a partial dissociation, indicating that it is a weak electrolyte. And so I went ahead and wrote down some of the solubility rules that I was referring to in the previous video, and also wrote down some of the common strong acids and the common strong bases. And so I'm going to go ahead and zoom out, and I want you guys to either take a snapshot or write these common strong electrolytes in your notes. I'll go ahead and go over it very quickly. And so common strong electrolytes are ionic compounds that either contains a group 1A element, perchlorate. And so perchlorate is ClO4 with a negative charge. That's a polyatomic ion. Nitrate is NO3 with a negative charge. Once again, that's another polyatomic ion. And your common group 1A elements are, for example, hydrogen, lithium, sodium, potassium, and the list kind of goes on. So you can go ahead and look at the periodic table for that full list. And so ionic compounds that contains chlorides, bromides, iodides are typically strong electrolytes, except when they're paired with silver, copper, lead, and mercury. Specifically those ionic forms. I'm just going to go ahead and erase my markings. I want to keep this as clean as possible. And sulfates are also strong electrolytes, except when they're paired with what I've listed down. So if you have like calcium sulfate, strontium sulfate, barium sulfate, lead 2 sulfate, mercury 1 sulfate, and silver sulfate, all of those are actually precipitates. And so since they're precipitates with sulfates, since they form a precipitate, if those ions are paired with sulfate, then it wouldn't be a strong electrolyte. And so this whole block is coming from your solubility rules. Now, for strong acids, I didn't really change too much from what I wrote down in the previous video. I just went ahead and reorganized it. So here we have our hydrochloric acid, hydrobromic acid, hydroiodic, sulfuric, nitric, chloric, and perchloric acid. And so if you look at these strong acids, notice that they kind of overlap with, for instance, some of the solubility rules. So like hydrogen, right? Chlorides, bromides, iodides. So here we see that again. Sulfates, right? And so I just wanted to reiterate those points just so you have a stronger list, a stronger resource of determining whether an electrolyte is a strong electrolyte or not. And just to complete the picture, sulfate is SO4, 2 negative. That's a polyatomic ion. Also, there's strong bases, so calcium hydroxide, strontium hydroxide, barium hydroxide, sodium hydroxide, potassium hydroxide, and lithium hydroxide. And so all of these compounds are going to be, they're going to act as strong electrolytes. So if you place them in water, they're going to separate 100%, producing a cation and anion that will enable electricity to be conducted. And so I did put in a little note here. There are so many more compounds that can act as a strong electrolyte. Um, there's no way that I can list all of those compounds in one page. And so we're just going to work with what we have over here. So go ahead and either pause this video or take a snapshot or write all of this down on your notes so that way you guys have this reference on hand. And so for common weak electrolytes, once again, this is just a super short list. HF, hydrofluoric acid, it's a common weak electrolyte. Acetic acid or vinegar is also a common weak electrolyte. And so recall that acetic acid can be written in two ways. So both of the items I've highlighted, they do represent acetic acid. And so organic acids are just basically molecular compounds that's carbon-based. So if you look at acetic acid, that's a carbon-based compound. And it does have ionizable hydrogen. So for example, this hydrogen that I'm circling and this hydrogen that I'm circling can separate from the anion of that chemical formula. And so there's a whole class of organic acids. There's no way for me to, once again, list all of them down. And so let's go ahead and move on to the next item. And so ammonia, or NH3, is a common weak electrolyte. And you also have some common weak acids. So for example, here we have phosphoric acid, carbonic acid. This is going to be chlorous acid. Here we have HSO4, hydrogen sulfate. Here we have nitrous acid. And here we have sulfurous acid. So all of these are going to be our common weak acids, and they're going to partially dissociate in water, producing a very weak conduction of electricity, just because there's not a lot of ions that's present in that solution. Okay, so once again, go ahead and pause this video, write this information down, or go ahead and take a snapshot of this if you are if you have that ability in your computer. And then we're gonna go ahead and go through some examples, and we're gonna use this list to basically predict whether or not a compound is going to be a strong electrolyte, weak electrolyte, or a non-electrolyte. And so for non-electrolytes, remember, they're mostly compounds that have nonmetals. And we'll look at a few examples. All right. And so we're going to go ahead and identify whether or not the solute is a strong electrolyte, weak electrolyte, or non-electrolyte. And so before we begin, to help you, to guide you as to how you can whittle these choices down, we're going to go ahead and use this flowchart, right? And so here we have a solute, which is going to be the given. And then we want to first identify if it's a non-electrolyte or if it's an electrolyte. And if it is an electrolyte, then we need to identify if it's a strong or a weak electrolyte. Okay. And so the way that we figure out whether or not this first compound KBr is an electrolyte or non-electrolyte is by looking at the position of where those elements are in the periodic table. And so notice that potassium is a group 1A element. So it's a group 1A metal. Okay. And bromine is a nonmetal. So it's found to the right of the staircase. And so if you recall, the staircase represents all these semi-metals or the metalloids in the periodic table. So anything to the right of that is going to be a nonmetal. Anything to the left of that staircase or where your semi-metals or metalloids are found, that's going to be your metals. And so since we have a metal to a non-metal, this is telling us that this is going to be an electrolyte. So KBr is an electrolyte because we have a metal to a non-metal. And so now that we know that it's not an it's not a non-electrolyte, we need to determine if it's a strong electrolyte or a weak electrolyte. And so to determine if it's a strong or weak electrolyte, we're going to go ahead and use this chart. And so we're going to look at the first element, which is potassium. So it turns out that potassium falls under these this specific rule. So if ionic compounds contain either hydrogen, lithium, sodium, potassium, then it's a common strong electrolyte. And so just through that justification, we can go ahead and identify that KBr is a strong electrolyte. And how I'm going to write strong electrolyte, just because it's such a lengthy word to write, I'm just going to abbreviate that as SE. So SE is strong electrolyte. And for weak electrolyte, I'm going to abbreviate that as WE. And then for non-electrolyte, I'm going to abbreviate that as NE. Okay. And so I'm going to conclude that since potassium is a group 1A metal, it is going to, KBr is then going to be a strong electrolyte. So it's an SE. All right, so let's go ahead and look at this second example. Sodium sulfate. And so very similar to what we did in the first problem, for this second problem, we're going to first identify if Na2SO4 is a non-electrolyte or an electrolyte. And looking at the first element, sodium, sodium is once again a group 1A metal. And sulfate is a polyatomic. And so since we have a metal to a polyatomic, this is going to fall under electrolytes. And so now that we have identified that Na2SO4 is an electrolyte, we need to determine if it's a strong electrolyte or a weak electrolyte. And so if we look at our list of strong electrolytes, if your ionic compound contains sodium, then that ionic compound is going to be identified as a strong electrolyte. And so our final answer is going to be Se. Let's go ahead and take a look at the next example. And so here we have carbon, hydrogen, and oxygen. And so we want to identify where all three of these elements are located and whether or not they're metals or nonmetals. And so if you look at your periodic table, carbon and oxygen is to the right of the staircase. So for sure, carbon and oxygen is a nonmetal. Hydrogen, however, is found on the top left corner of the periodic table. And it's right above lithium. And so one might think that hydrogen, since it's technically to the left of the staircase, is going to be a metal. However, it's just one of those exceptions. So hydrogen is not a metal. It's actually a gas, H2 gas. So remember your diatomic gases. And so therefore, since hydrogen is not a metal, it's going to be considered a nonmetal. And so all three of these are nonmetals. And if all three of your elements are nonmetals and they're not part of your weak electrolyte list, then therefore C12H22O11 is going to be a non-electrolyte. And once you've identified if it's a non-electrolyte, you really don't need to look at this list, right? I mean, this list is only to differentiate strong electrolytes from weak electrolytes. So looking at our next example, so we have LiOH. Once again, the first thing that we need to do is determine if it's an electrolyte or a non-electrolyte. And so since lithium is a metal, so Li is a metal, and OH is a polyatomic. When you have this combination, metal and polyatomic, then this tells us that LiOH is an electrolyte. And so since it's an electrolyte, we need to determine if it's going to be a strong electrolyte or weak electrolyte. And so we can go ahead and look at the list for strong electrolytes, and we see lithium present. And so if you have a group 1A element as part of the ionic compound, then it's going to be a strong electrolyte. We also have another justification. LiOH is a strong base. And so both of those two together informs us that LiOH is going to be a strong electrolyte. Okay, so hopefully you guys are kind of understanding my train of thought, the logic. So let's go through the rest of the examples. Here we have H2O, so that's water. And so if we look at the two elements that's present in this compound, or in this molecule, I apologize, it is, they're both nonmetals. And since they're both nonmetals, and it's not found in our weak electrolyte list, therefore, this is going to be a non-electrolyte. And once you've identified if it's a non-electrolyte, you don't really need to do anything else to it. All right, so let's go ahead and look at carbon. Let's look at the next example. Notice that there's carbon, there's hydrogen, there's oxygen, and then there's another hydrogen. So very similar to everything that I've highlighted above. Notice that all elements are going to be found either on the right side of the staircase in the periodic table, indicating that they are nonmetals, or in that they're in that top left corner because it's a hydrogen. And so here in this case, since we have hydrogens and oxygens and carbons, all of them are nonmetals, and therefore this is going to be a non-electrolyte. Okay, so looking at our next example, here we have HI. And so, it's very tempting to say that, oh, look, we have hydrogen, which is a nonmetal, and here we have an iodine that's a nonmetal. However, if you look at our list, HI is a strong acid. And so since it's under strong electrolytes, that pretty much answers the question. Let me just erase this part right here. Okay. So looking at our next example, we have NH3. And so once again, it's very tempting to say that, oh, look, we have nitrogen and hydrogen. And so therefore, this must be a non-electrolyte because both elements are nonmetals. Unfortunately, we cannot make that conclusion because NH3 is actually found on the list of common weak electrolytes. Okay. And so since it's a common weak electrolyte, we can go ahead and just put in We. So for some of these compounds, you really have to check both lists before you arrive to your final answer. Right, and so it doesn't hurt to kind of double check before you lock it in, so to speak. And so the next compound is going to be calcium nitrate. And here, if we identify where calcium is located in the periodic table, it's found on the left-hand side of the staircase. It's underneath group 2A. And so therefore, calcium is going to be a metal. And NO3, or nitrate, is a polyatomic. And so if you have a metal and a polyatomic, then we know that this is an electrolyte. And so what we need to do is identify whether or not it's a strong electrolyte or a weak electrolyte. And so once again, we can go ahead and look at our list. And so we're looking, since our compound is calcium nitrate, we're going to see if we have nitrates or calciums on this list. So it turns out right here, ionic compounds that either contain a nitrate is going to be a common strong electrolyte. And so we didn't really need to look very far to determine that calcium nitrate is a strong electrolyte. Okay. All right, so the last example on our list is going to be HC2H3O2. So here we have a hydrogen, a carbon, a hydrogen, and an oxygen. And so one might assume that this is a non-electrolyte because they're all carbons and hydrogens and oxygens. However, once again, it doesn't hurt to check all of your lists, all of your compounds. And so you really want to find the compound that we're looking for in the strong acid list. However, it is found in the weak electrolyte list. And so here in this case, if we have HC2H3O2, that compound is going to be a weak electrolyte. And so we're going to go ahead and put in We. Okay. And so hopefully you guys are able to understand how I'm using this list to help me differentiate between strong electrolytes and weak electrolytes. So if you haven't written this stuff down on your notes or took a snapshot of it, go ahead and do so. You can always rewind the video if you need to. All right. So we're going to go ahead and discuss levels of saturation. And so when we're talking about the saturation of solutions, there's three terminologies that we have to go through, that we have to talk about. So the first terminology is unsaturated solution. And so you will have an unsaturated solution if more solute can be dissolved in the solvent. So what does that mean? So let's just say that we have a pure sample of water. And what we're going to do is we're going to sprinkle in some sodium chloride, some salt. And so we're going to put in some salt, and then we're going to go ahead and take this glass stir rod and swish it around to mix this solution. And so when you have salt crystals in water, you can actually do this at home. You can go ahead and take maybe just a little bit of a small amount of salt and then just add it in to a small container of water and just mix it with a spoon or a fork. You'll see that when the solution is stirred, these crystals are going to dissolve. And so if all of the crystals dissolve, then that solution has not reached saturation. In other words, more solute can be dissolved in the solvent. And so after the first addition of salt, we stirred it around. And so keep in mind that there's already one addition of NaCl that's dissolved in this water. What we're going to do is we're going to add a second addition of the salt, and then we're going to stir it once again. And if you were to add some more crystals of salt, and after you stir it, you see the crystals disappear, that still means that it still means that your solution is unsaturated. And so we can go ahead and do a third addition. Okay. So this is the third time that we're adding salt into this solution. And let's just say that after a third time, most of your crystals dissolve. However, there's a few that doesn't get dissolved. I'm not too sure if you guys have experienced that in your life. And so maybe when you guys are like mixing, I don't know, like coffee and sugar and all that stuff, if you add too much sugar, you'll still have the sugar granules, resting at the bottom. And so what that's telling you is that that solution cannot hold any more solute in the given amount of solvent. So at that moment in time, your solution is now saturated. And so a saturated solution refers to the maximum amount of solute that the solvent can dissolve. And so, this is the scenario where you add a whole bunch of salt, and then let's just say that you stir it with this glass stir rod. And after you stirred your solution, most of the particles was able to dissolve. However, there's maybe like a few granules that hasn't dissolved. And at that moment in time, you would say that this solution is saturated. Okay? Hopefully that makes sense. Last but not least, you can get a supersaturated solution. And supersaturated solutions has been used to in industry, specifically, I guess a low-hanging fruit would be rock candy. And so you guys can actually do this at home. You can take, some water and boil it and just add a whole bunch of sugar. And so the heat from the hot water is able to dissolve more solute than it should be able to hold at room temperature. And so what happens with the supersaturated solution is that you have more dissolved solutes than normal solubility typically allows. And you can get a supersaturated solution when you heat your solvent and then allow it to cool down. And then once it's cooled down to, for example, room temperature, that solution becomes really, really unstable. And if you were to add really almost anything to it, crystals can start forming. And so I want to go ahead and play a quick YouTube video that demonstrates the effect of a supersaturated solution. Okay. Let me see if hopefully I'm pressing the right thing. There it is. All right. And so inside is dissolved sodium acetate, and it's a supersaturated solution. So this person is going to go ahead and add just a seed crystal of that acetate, and then notice that you guys see these crystals form from that seed crystal. And so this is what happens when you create a supersaturated solution. Now for rock candy, it's pretty much the same effect. You can go ahead and put a string inside that sugar water solution, and if you allow the solution to cool down after it's been heated, then you'll start seeing these crystals form on the string. And then you can go ahead and color it to whatever color you like, and you just basically made rock candy. Cool. And so the last time that I want to cover for supersaturated solution, or I'm sorry, not supersaturated solution, but saturations of solution, is one specific problem. Okay. So at 40 degrees Celsius, the solubility of potassium bromide is 80 grams per 100 grams of water. We're going to determine if the solutions are unsaturated, saturated, or supersaturated. And so what this problem is basically describing is that 80 grams per 100 grams of water defines saturation. Okay. So if we have 80 grams of KBr per 100 grams of water, we would say that solution is saturated. So we've reached the maximum amount of solute that can be dissolved in the solvent. And so let's go ahead and look at question A. If you have 60 grams of potassium bromide and you add it to 100 grams of water, would the solution be saturated, unsaturated, or supersaturated? What do you think? So if you had said unsaturated, then you're correct. And so if you have 60 grams of KBr in 100 grams of water, the ratio is basically 60 over 100. And remember that the saturation is 80 out of 100. So since 60 out of 100 is less than 80 out of 100, then this would be an unsaturated solution. All right, so let's go ahead and look at the second example. So if we have 200 grams of potassium bromide and it's added to 100 grams, is this solution going to be unsaturated, saturated, or supersaturated? And so since we're adding more solute than what it can typically handle, so to speak, we're going to say that this solution is supersaturated. And so finally, or I'm sorry, not finally, for part C, we have 79.8 grams of potassium bromide, and we're going to add that to 100 grams of water. So 79.8 grams is very, very slightly below 80, but it's very close to it, right? It's only about zero point 0.2 grams away. And so we can go ahead and say that this solution is probably going to be saturated, or it's near to the point of being saturated. So last but not least, for part D, we have 25 grams of potassium bromide, and that's going to be added to 50 grams of water. And so here in this case, we have 25 over 50, which is essentially 1/2. If you reduce that down. Now, if you look at our original saturation limit, this is telling us that we have 80 grams over 100. And so we can go ahead and reduce this to 8 over 10. And 8 over 10 can further be reduced to 4 over 5. Oops. And so if you plug this into your calculator, 4 divided by 5 is going to be less than 1 over 2. So 1 over 2 is like 50% or 1/2. I'm sorry. So 4 or 5 is going to be greater than 1/2. And so let me just plop this over here. So 1/2 is less than 4 over 5. And since this value is less than 4/5, then this is telling us that this solution is unsaturated. Okay, so hopefully through this video you guys understand how to identify if a solute is going to be a strong electrolyte, weak electrolyte, non-electrolyte. And hopefully you guys understand what it means for a solution to be saturated, unsaturated, and supersaturated. And so in the next video, we're going to go ahead and talk about why solutions or how solutions form. In other words, we're going to see if a solution is homogeneous or heterogeneous. And basically, we're going to try to understand the underlying factors that will allow a specific solute to either be soluble or insoluble in solution. And then we're also going to talk about the other factors that affects solubility, such as temperature and pressure. All right, guys. I'll see you in a bit.